In this video, we're going to be solving systems of linear equations. Problem 1 involves a 2x2 system, variables x and y. So these two represent, the graphs represent lines. So we were to graph any two lines, they're either going to intersect at one point. We have one solution. The lines will be parallel, no intersection point, no solution. Inconsistent system. Or the lines could coincide, intersect at many points, so to have an infinite solution set. So that means that we can have either one solution, one ordered pair, we could have no solution, or we can have a infinite solution set. Same sort of thing in the second one, even though in the second one we're talking about planes, because we have three variables, three equations and three variables. But the same things that happen. We can either have one solution, no solution, or an infinite solution set. So by the elimination method, what we do here is use properties of equality. If I have A equal to B and C is equal to D, I can add the left side of these two and the right side. So I can have A plus C will equal to B plus D. I can also subtract these. A subtract C will equal to B subtract D. And I could add multiples of this also and still have equality. So we're using properties of equality. So the objective then, we have two variables, x and y. So the objective is to use these properties of equality. We can add the two equations. We can multiply one equation by a number and add. So the objective is to reduce it down to one variable. It's easier to solve it if we have one variable. So let's get rid of this y here. I'm going to multiply the first equation by 4. So it's going to be 4 times the 2. X is 8x. 4 times the minus y will be minus 4y. And 4 times 3 will give me 12. And then we're going to add them. Let's do it this way. 4 times 2 is 8 and 5. So it's 8x and 5x is 13x. And then minus 4y and a 4y cancel out. 3 times 4 is 12. 12 and 40 is 52. Now we just solve for x by dividing by 13. This cancels out. I get x is equal to 52 divided by 13 is 4. So I know that x is 4. Now I could get the y by eliminating the x. So I could multiply, say, this by 5, the first equation by 5, and the second equation by negative 2. So 5 times 2, x is 10x, minus 3 times 5x is minus 10x. Those would cancel, and I would have just an equation involving y. And that would complete the elimination method. However, to shorten this, because I know the value of x to be 4, I could just put the 4 right here with this x here in this equation, or in the second equation, didn't matter. Say 4 times 2 there would be 8 minus y equal to 3. And then bring this over to this side. That'll give me 8 minus 3 is 5. Take the y over here, minus y over here, I get y equal to 5. So the solution set is x equal to 4, y equal to 5. Sometimes I'll write down a solution pair, because if I were to graph the two lines there, that's what these represent, the lines, they would intersect at the point 4, 5. So sometimes you'd give the answer this way as an ordered pair, or you can just say x equal to 4, y equal to 5. And there's other methods. Here we're using the elimination method. We're adding the two equations, or multiplying the one equation or both equations by a number and adding, so we can cancel the x or the y, and isolating that variable and solving. There's also methods involving determinants, Cramer's rule. There's some matrix methods you can also use, but here we're focusing on the elimination method. So what did we do here? We had a system of two equations with two unknowns, and using this elimination method, we reduced it down to one equation right here, one variable. We got the answer to that variable, and then we plug it in to get the answer to the value of to the other variable x or y. Same sort of thing here. We have three variables, so we want to try to reduce this down to 2 and then eventually down to 1. So what we'll do here is I can add the first equation and the second equation, and that's going to cancel the z. Minus z and z cancel, so let's do that. This will give me this, and this is 4x minus y and 4y is plus 3y, and then 4 and 4 is 8. And then I would take the second and the third equation and eliminate the same variable, so I can get the same variables x and y. But notice that the third one is missing the z. So I could just put these together. Got 12x plus 9y is equal to 0. So now I got a problem like number 1. I have an x and a y, so what I can do here is use the elimination on these two equations, solve for the x and the y, and then plug into either equation number 1. Once I get x and y, plug into number 1 or 2 and get the value of z. So the same sort of thing. I'm going to use elimination. So let's see, I got a 4x and a 12x. So if I multiply the first equation by -3 and then add, notice -3 times 4x is minus 12x, and 12x will give me 0. And then -3 times 3y is minus 9y, and 9y is 0. So I got 0 plus 0. And then I got -3 times 8 is a minus 24, and 0 is minus 24. 0 plus 0 is 0, and 0 is equal to -24, which we know is not true. So whenever you're solving a system, whether you're using this method or using the substitution method, which can also be used to solve these systems, and you get a contradiction, something that cannot happen, 0 cannot equal to -24, this one has no solution. What happens here again is there's no intersection. In this case, we're, in problem 2, we're dealing with 3 variables, so these are planes. But you still have the same sort of thing. The planes could be parallel and have no intersection point. So this one has no solution. Thanks for watching. We'll see you next time.